So we now talk about multivariate time series. So these are also called vector autoregressive processes. So time series is autoregressive and vector is for the multivariate processes. To start with an example, let us consider two processes whose price you think impact each other. For example, you can say that price of cast iron and price of wrought iron are linked to each other. So first, let us suppose this is the series for cast iron prices. So T stands for today. So today's price depends upon yesterday's price and day before yesterday's price for cast iron. Then you can say it also depends upon past prices of wrought iron. So yesterday's price of wrought iron and day before yesterday price of wrought iron. So wrought iron is YT minus 1 here and YT minus 2 here. So I've just put some coefficients with plus or minus sign, nothing special about them. So obviously you cannot put today's cast iron price as a function of today's wrought iron price because both these prices are discovered at the same time. Now similarly you could talk about the wrought iron. So say today's wrought iron price Y of T depends upon wrought iron price 1 day lag, that is one period. I mean, with one lag you can put lag as days or specific periods like months. It's up to you. So it depends upon the first lag and a second lag, that is say yesterday and day before yesterday, or if you have collected prices in months, last month and the month before that month. But you can say this wrought iron price also depends upon the cast iron price, so you are also incorporating cast iron price of yesterday and cast iron price of day before yesterday. And then you have these two error terms, or you can say innovations or shocks. These are correlated. So just like in correlated random walk, these are drawn from a normally distributed matrix with mean 0 and variance given by some covariance matrix sigma. So this is a standard vector autoregressive process. So let us write down in matrix form because we are going to analyze it in matrix form. So this xt yt just comes out like this. So its coefficient matrix is just the identity matrix 1 0 0 1. This 4 7 I copy right here. Then again this matrix 0.4 minus 0.2 minus 0.1 is right here, 0.6 is right here. Then we have this. So this is first lag. This is multiplied with xt minus 1 and yt minus 1. xt minus 1 and yt minus 1, first lag. Then this is the second lag. So minus 0.4 plus 0.6 and then minus 0.2 is right here, 0.2 is right here. This is second lag and these are correlated error terms. So notice that this matrix is a 2 by 2 identity matrix. This is 2 by 1, 2 rows and 1 column. This is again 2 by 2. This is again 2 by 2 matrix. And this is 2 by 1 matrix. So this is a standard 2 process. So say if you want to add a third lag, say now you're interested in steel and you think the steel price also depends upon cast iron and wrought iron price, and you want to incorporate steel. So then you incorporate a new variable zt. You write it equation, it depends upon zt minus 1, it depends upon zt minus 2. Then you can also incorporate xt minus 1, yt minus 1, xt minus 2, yt minus 2, and then you can incorporate zt minus 1 in this equation. So in this equation you can put in zt minus 1, zt minus 2. In this equation you can put zt minus 1, zt minus 2. So you can complicate as much as you want to, but to incorporate variables it is best to see it in matrix form. So say you want to incorporate one more variable z of t, then you make this a 3 by 3 identity matrix. This 2 by 1 now becomes 3 by 1. Then this will become a 3 by 3 matrix. You will add one more constant right here, say 1. This will become a 3 by 3 matrix. And you will have another variable here, zt minus 1. This will again become 3 by 3 matrix. You will have another variable zt minus 2. Then you will have a correlated random term, this. So to make this 3 by 3 matrix, you have to add one more row and one more column. Here again you have to add one more row and one more column. And once you add one more row, then that will link zt minus 2 with xt minus 2 and yt minus 2. So you can make any such number of correlated random processes or vector autoregressive processes. So now we want to write it in terms of a vector. So say this vector yt is k by 1 vector. So this is k by 1 vector, just like this was 2 by 1 vector. This is the constant matrix, which is again a k by 1 vector. This a1 is just like here, it is a 2 by 2 matrix here. This is k by k matrix here. It's a2, the second lag matrix. So for example, this is the second lag matrix, so t minus 2. So this is yt minus 2. This is yt is xt yt. This is t minus 2. Similar t minus 1. So this is again k by k matrix. And this is error terms. This is again k by 1 matrix, which is drawn from a, this k by 1 matrix is drawn from a normal random. But now we have a covariance matrix sigma. So this is the story. So this was special example of k equals to 2. And you can make as much new variables as you want to. You can add as many variables as you want to. Yeah, but in a previous lecture I had warned against adding more and more variables. So you should anyway see the lecture series on variance and covariance matrix and qualitative judgments on it. So the same idea which I expressed there about adding more variables makes sense here also. So coming back to this lecture, now you can construct a Lag polynomial. So what you do is you have the identity matrix right here. So this is the identity matrix. This one I have copied here, and then you subtract from it matrix A1. So you're bringing everything on the left hand side, just like a common algebra. Instead of yt minus 1 you write z, instead of yt minus 2 you write z square, and so on. So this will give you a Lag polynomial. This is Lag polynomial in matrices. So this should not be 0 inside the unit circle. So not be 0 inside the unit circle means that if you find the roots of this Lag polynomial, the roots have to be, the modulus of the roots has to be greater than 1. So this was precisely the same case we had in single variable univariate time series. So what we have in univariate time series also holds for multivariate time series, although we are using matrices. Now the beauty of R is you don't have to do anything. You just need to know this and R will compute it for you. For our purposes, the R uses a root test, but what it spits out is the eigenvalues of the coefficient matrix. So we're going to talk about this coefficient matrix in a minute. And R just shows that the values of this coefficient matrix is less than 1. So the command in R is roots. So this command you will see later on. I have already put in a code. So in the next video when we simulate this, we will work with this roots command. So it will show it as less than 1, and that will mean it's a stationary process. So we are going to be worried about eigenvalues rather than actual roots. So what is a coefficient matrix? So the coefficient matrix for this process is right here. So let us see how did this come about. So let us do step by step. So this is 1. So we are corresponding to the variable x of t now. So we are working with variable x of t. 1 is here, then you take 0.4 from here, then you take minus 0.4 from here, and bring everything on the left hand side. So 1, it will be minus 0.4, then this minus will become plus. When you take it on the left hand side, it will become plus 0.4. Now you focus on this variable yt. So you have 0 here, 0, then you have minus 0.2 here and minus 0.2 here. Bring in them on the left side, it will become 0, plus 0.2, plus 0.2. Now let us focus on this variable here. You have 0 here, and then you have 0.1 here. So 0 plus 0.1, and then this 0.6 is there. This will become minus 0.6. You take it on the left hand side, and that's what we have. 0 plus 0.1 minus 0.6, and then you have 1 here. This 1, then this is 0.6. Take it on the left hand side, it becomes minus 0.6. And then you have 0.2 here, take it on the left hand side, it becomes minus 0.2. So this is it. So this is the coefficient matrix, and this is precisely I have computed for this. So what is this? For k equals to 2, our example, this thing is precisely this matrix. So if I want to simulate this process, which we are going to do in the next lecture, we have to give two things. We have to first tell our system this coefficient matrix, because this coefficient matrix basically captures this identity and all the coefficients. So first thing you want to give is the coefficient matrix. So coefficient matrix is capturing all the coefficients. It's capturing this, it's capturing this, and obviously capturing the identity matrix. The second obviously you want to capture is these constants. So you will have an input of a constant matrix. And third thing is that you have to draw these random variables from a normal distribution. So a normal distribution, this is a correlated random walk. Or you can say correlated white noise essentially. So it is coming from this covariance matrix sigma. So you have to put in this covariance matrix sigma. So these are the three inputs for the simulation of a vector autoregressive process. So we are going to do it for this particular equation, but as I told you, you could expand it to as many variables you want to.